In today's lab, we'll be studying the inverse square law of light. But before we do that, we need to define the power and the intensity. So the power is equal to the light energy divided by time, and the intensity is equal to the power divided by surface area. So for a point source of light, the light is going to spread out evenly in all directions, creating a sphere with a radius of r and a surface area of 4 pi r squared. And this is where we get the inverse square law. We have the intensity is proportional to 1 over r squared because we have surface area, 4 pi r squared, in the denominator. So then intensity is proportional to 1 over r squared, or the distance squared. And practically this just means that the farther away you get from any light source, the intensity or the brightness of light is going to decrease according to 1 over the square of the distance. For the experiment, we'll be using two white LEDs. One will be our point source of light, and the second will be our detector. So the point source, that makes sense. LEDs produce light. But for the detector, when you shine light on an LED, it actually produces a small amount of electric current inside the LED. The photons hitting the LED cause the electrons to flow and produce a current that's directly proportional to the light intensity. However, this current is a bit too small to measure accurately with the multimeter in our lab kit, so instead we can measure the voltage, and since voltage and current are directly proportional according to Ohm's law, we can say then that the voltage is also directly proportional to the light intensity and can be thought of as a measure of that light intensity. The first step, as usual, is to find our resistor. So for this circuit we need a 470 ohm resistor, and this will limit the current flowing through our LED and prevent it from burning out. As I've explained in previous videos, you can identify your resistor from the color code printed on it, and in this case a 4-color code 470 ohm resistor is yellow, purple, brown, and then it does have a gold tolerance band of plus or minus 5%. Unlike the previous labs, for this circuit we don't really care about the exact resistor value. We just need it to be the 470 ohm resistor so that it limits the current to the LED the proper amount. And if you're not really sure which resistor it is, you can double check it with the multimeter. Next we need to build the circuit, and for that we'll use the resistor, the potentiometer, which is an adjustable resistor, the 9-volt battery, and then a white LED. Now all of these LEDs look identical, they're all transparent, so you won't be able to tell just by looking at them which one is which. But once we build the circuit, then we can test them and figure out which one is the white one. Alright, so this is the circuit, and going from left to right we have the battery here with the red positive battery wire going into the red positive power rail. Then the black negative battery wire is going into the blue negative power rail. Then we have the potentiometer, and I'm going to go ahead and remove this. It'll make it a little easier to show you what I've done with the jumper wires. So again, going left to right, we have the jumper wire here going from the blue power rail into the first hole on this row. And then at the other end of that row, I have another jumper wire going down across this center gap of the breadboard, and then this other jumper wire coming across here. So this is all the negative battery wire. It's all connected right there, and this connects it to the LED. Then back up here we have another jumper wire going from the red power rail into the first hole on this row. So I skipped a row, and then I had this one, which is connected to the red power rail. Now this row that I skipped, at the other end of this I have this yellow jumper wire that bridges the gap across the center of the breadboard, and then we have the white jumper wire that goes across here and connects to the same row as that end of the resistor. Then the other end of the resistor is connected to the LED, and that completes the circuit. Now when you look at the potentiometer, you'll notice that it has 3 pins, and those 3 pins correspond to the 3 rows right here. And when you place it in the breadboard, you need to make sure that each of these 3 pins goes into a separate row. So the outer pins should go into the same rows as that jumper wire and that jumper wire, and then the middle one should be in the same row as that little yellow jumper wire right there. So if I place this right here, I'll just line up those 3 pins, and that will fit into this gap right there, and that completes the circuit. The last thing I need to mention with the circuit is the LED polarity. So LEDs have a positive and a negative lead. The current only flows through them one direction, and if you straighten out the leads, you'll see that one of them is longer than the other. The long lead is the positive lead, and in this circuit you want to put the positive lead up here connected to the resistor, and the negative lead is connected down here to this wire that goes back to the negative battery wire. Now that we've completed the circuit, we can turn the potentiometer knob and light up the LED. And it looks like the LED was a red one, not a white one, so I'm going to have to swap that out and find the white LED. Now we've got the white LED in there, and that's it. So until we're ready for the circuit, I'm going to unplug the battery. We don't want to waste power until we're ready for it. Next, we need to make our light detector, and for that we need another white LED and some modeling clay. But before we make it, we need to find that white LED. We don't want to accidentally make it with a colored LED and then it ruins our experiment. So I'm going to find the white one and then test it in my circuit to make sure. So here's my original white LED. That's the point source LED. And then here is the second one that we'll use for the detector, and that one is also a white LED. To make our detector, we're going to make a small pillar out of the modeling clay. So I'm just going to squish this up until I have something roughly about this size. Doesn't have to be an exact size or shape, but you want something about that big. So if I turn this around, you can kind of see how big I've made it, and then we need to poke a hole in it. So to do that, I'm going to use the back end of this pen, and I'll just press it right through the clay like that, poke it out on the other side, and I'll scrape that clay back off and just stick it to the bottom. So now we've got this clay with a hole in it, and that hole will be for our LED. So what you want to do is place the LED just inside the hole, so it's just barely in from the edge, and then we're going to press the clay in around it so that it holds the LED in place. Then you want to check by looking in the hole and making sure that the LED is pointing straight out and isn't at an angle, and also that the clay isn't obstructing the view of the LED. If you need to, you can use something like this pen cap to clear out the hole around the LED and just make sure that it has a good clear view and isn't obstructed by the clay. Next, we need to bend the LED leads out at an angle like that so that they're separated from each other. We're going to connect alligator clips to these next, and we don't want them close together where the alligator clips will touch each other. Before I do anything else with the detector, I need to tape this ruler down to the table, and this will provide our markings to measure the distances in our experiment. Notice when I did this that I made sure to not cover up any of the centimeter markings. We're going to need these for the experiment, so make sure you don't cover those up with the tape. Now we need to place the clay pillar with the detector LED at the 0 centimeter mark. So that LED that's inside the clay, the front of it needs to be lined up pretty close to the 0 centimeter mark. And I've marked it here on the outside of the clay roughly so that I know where it is, and then I can line that spot up with the 0 centimeter mark. You should also press the clay down onto the table so that it makes good contact and it isn't easily tipped over. Now grab your multimeter, and we're going to use this to measure the voltages. So turn the dial to the 200 millivolt range, and then make sure the probes are in the correct port. So we want black in COM and red in V for volts. Now just grab 2 alligator clip wires, and we'll use these to connect the multimeter probes to the LED leads. If you happen to connect them backwards, then the voltage will show up as negative, but either way it'll work just fine. You can either switch the leads or just treat it as positive. You can see that I've connected the LED leads to the multimeter probes using these 2 alligator clip wires, but just make sure when you do this that you haven't messed up the angle of the LED. So look inside there and make sure that the angle is still good, and then adjust it if necessary. Now to complete the setup, we need to prop up our breadboard so that it aims at the detector. And to do this, we're actually going to tape the battery to the back of the breadboard. So I'm just going to grab some electrical tape and wrap that around there so that it holds the battery to the back of the breadboard. So not only does this allow the breadboard to stand up on its own, but it will also make it harder to accidentally unplug the battery wires. The last thing we need to do is make sure the 2 LEDs are at the same height. And we can do that by just bringing the breadboard right up here in front of the detector and seeing if they match up. And it looks like they do. But if they didn't, then I might need to adjust the LED in the breadboard up or down to match the LED in the clay pillar, or we could adjust the clay up or down to match the one in the breadboard. However, if you adjust the one in the clay, you will need to make sure that the angle of the LED is still correct. Now we're ready to collect our data, and for that we need to shut off all the lights in the room. However, in order to film this, I'm going to need to leave some of my lights on. I'll shut off as many as I can and aim the remaining lights away from the sensor, but for you I would recommend that you turn off all the lights that you can, close the windows, close the blinds, and make the room as dark as possible. If you need to see during the experiment, there's a light button on most multimeter displays, so you could use that to read the value or use a small flashlight or something if you need to write things down. All right, now that the lights are off, or in my case, most of the lights are off, we can measure the background light intensity. So ideally, the multimeter should read 0 right now, and you can see that it's pretty close with mine. It's fluctuating right around 0, goes up to 0.2, maybe 0.4, but it usually goes back to 0, so I'm going to call that 0. However, if you found that it was not 0, let's say it was around a half of millivolts or 1 millivolt, then you might need to subtract that value from all of your future measurements to compensate for the lack of total darkness. In my case, I played around with the position and the angle of the remaining light sources so that the background measurement was approximately 0. Now we need to calibrate our source LED, so I'm going to plug the battery back in so that it turns the light on, and then just line it up right here at 30 centimeters. And I'm going to use a straight edge for this. I'll use a protractor. You can use whatever you like. I'll just use that to line it up exactly at 30 centimeters. So the front of that LED is right at the 30 centimeter mark. Then, without moving the breadboard very much, just point the LED right at the detector so that the brightest part of the light is shining into that hole and is reaching the detector LED. That looks good. Then, without moving anything, adjust the brightness with the potentiometer knob until the voltage measurement says approximately 1 millivolt. So we've got 0.9 right now, back to 1 millivolt. It's pretty close. I'm going to turn it up just a little bit. That looks pretty good. So we got 1 millivolt, and again, just make sure it's still pointing directly at the detector. And it looks like I got it offset just a little bit. So that looks good. It's pointing directly at the detector, and the voltage measurement is roughly 1 millivolt. Now, for the rest of the experiment, don't change the brightness. We need that to stay the same, so the only thing we're changing is the distance between the source and the detector. Now we can record the distance and voltage measurements, and the first distance will obviously be the 30 centimeters. And we can just verify that it is still at 30 centimeters. I'll just grab my protractor. That looks good. And then make sure that it's still aiming directly at the detector, and it looks like it is. So our distance then is 30 centimeters, and then the voltage is whatever is on the multimeter. And it is oscillating somewhat, so maybe I'll just let it sit there for a second, see if it settles down. So we've got 1.1 millivolts. So 1.1 millivolts is the voltage, and then 30 centimeters is the distance. Then we're going to decrease the distance by 2 centimeters, so I'll adjust it now to 28 centimeters, and again use the protractor to line it up exactly at 28 centimeters. That looks good. And then I just need to aim it directly at the detector, and it looks like it is. And then I'll record the distance, 28 centimeters, and the new voltage, which if I just let it settle down for a second, is 1.3 millivolts. Then we'll again adjust it by 2 centimeters, so now the distance is 26 centimeters. Line it up with the straight edge, check the angle, make sure it's shining directly at the detector, and now we have a voltage of right around 1.5, maybe 1.6. It's at 1.7. Okay, so 1.7 millivolts, and then the distance is 26 centimeters. So each time you do this, just keep adjusting the angle of the LED and watch the multimeter display. So when you get the angle right, when you've aimed it perfectly at the detector, then you'll see that you have a maximum voltage then for that position. So then you can record the voltage and the distance. So we'll just continue this process. Our next position will be at 24 centimeters. Get that lined up here, aim it at the detector, and record the voltage. And we do 22, again line it up, aim it correctly, and record the voltage. And we'll keep doing that until we get down to 10 centimeters. After 10 centimeters, we'll proceed at 1 centimeter increments. The changes here will be much more dramatic than they were for the first part, and so we need a much finer precision to capture the changes in the data. Also, as the source LED gets closer to the detector, you'll want to take extra care to aim it properly. Small differences in the angle at this distance will have dramatic effects on the voltage. So just keep playing with the angle until you find that peak voltage, and then that's the voltage that you'll record for that distance. So after 10, we'll record the voltage at 9, 8, 7, 6, 5, 4, 3, 2, and then you can try to get to 1. You might not be able to, depending on how thick the clay is, but if you can, then that's probably about as close as you'll be able to get. For each one of these, as I said before, line it up with the straight edge, then adjust the angle so that it's aiming perfectly at the detector, record that peak voltage that you achieved with the proper angle, and then record the distance and that voltage. When you finish, there should be voltage and distance measurements from 30 centimeters all the way down to 10 centimeters at 2 centimeter increments. Then from 10 centimeters down to 1 centimeter, or as close as you can get, you'll have voltage and distance measurements at 1 centimeter increments. For the last couple measurements, depending on how bright you set your source LED, you may need to adjust the multimeter up to the 2000 millivolt range if the voltage crosses over the 200 millivolt threshold. When you do the analysis, you may find that the last couple points, the ones close to the detector, don't follow the inverse square law. And if that's the case, then just ignore those points, just exclude them from your curve fit. Hopefully you don't have to exclude more than 3 or 4 points, but if you do that, then the rest of them should follow the trend nicely. Also, don't forget, when you finish the experiment, make sure to shut off the multimeter and unplug the battery from your circuit. And that's it. So just make sure to read your instructions carefully. They will have more information than what is shared in the video, and good luck on your experiment.